Good evening, class. We are looking at section 3.3, derivatives of trig functions. Okay. All right, so besides what we have learned so far, we are adding more formulas, class. Just as an example, the derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of tangent is secant squared. Cotangent is negative cosecant squared. Secant is secant tan, and cosecant is negative cosecant cotangent. And here's the limits that will help us see the proof. So we're going to spend a couple of minutes proving those. Limit of sine theta over theta as theta approaches 0 equals 1. Limit of cosine theta minus 1 over theta as theta approaches 0 equals 0. So let's see how the proof works, and we take it from there. So first and foremost, I hope everybody remembers the unit circle. Okay, so let's just, here's the unit circle. Remember, x squared plus y squared equals 1. Generally is x minus h quantity squared plus y minus k quantity squared equals r squared, but this is a unit circle. Now, the limit of sine theta as theta approaches 0 is 0. In other words, sine of 0 is 0. For cosine is 1 because cosine of 0 is 1. Now we are looking at the proof for these two. We're going to prove the first one. And to prove the first one, this is the unit circle. And we are looking at just the first quadrant to make life easy. It's a portion of your unit circle, class. I hope you remember that. And any a point has coordinates cosine theta, sine theta. This is theta. I hope you remember that. And we choose the first quadrant to make life easier, and everything is positive, as you recall. Everything, sine, cosine, tangent, cotangent, secant, cosecant, all of them are positive in the first quadrant. So with that being the case, if you drop a perpendicular here, class, if you drop a perpendicular here, it becomes this one. And that basically becomes your sine. This arc, okay, is a central arc, and this is equal to theta. And then if you go up and you continue, this becomes your tangent. That's really the idea we are going to use here. So how do we prove? We are going to prove this one. How do we prove this one? I give you the synopsis of what is coming up, and I will explain it first, and then we'll see the details. Sine theta is less than theta is less than tan theta. Why? So pay attention to my explanation, everybody, and then I'll write it for you. But first, let's see if we can follow that. Again, remember, you have a unit circle. We are looking at only the first quadrant, okay? And we are blowing this part up, okay, this part into this one. Okay, in other words, let me just, so this is the part we are interested in. Okay, so unit circle. Okay, so if you drop a perpendicular here, BC, I hope you realize sine theta is BC, okay, the opposite, over the hypotenuse OB, which is 1. So sine theta becomes BC. Done. What about theta? Theta is the arc. Okay. Now, as you can see, the arc is larger than AB. Okay. And AB is the hypotenuse of this triangle. So AB has a larger length than BC, and arc AB is larger than both of them. Therefore, sine theta is less than theta. And what is this AD? This is the value of a tangent. First of all, why is that? Because tangent by definition is the opposite, AD, over the adjacent OA. OA is what? Is the radius, which is 1. So the tangent is equal to AD, and I hope you realize that the arc is less than AE plus EB, and in this small triangle, DE is the largest number, the largest side, because it's the hypotenuse. Therefore, the arc, which is less than AE plus EB, is less than AE plus ED, which is AD, which is the tangent. So that's, believe it or not, the synopsis of that. But let's again do the writing here. First, sine theta is less than theta. Take a look at the justification again. Sine theta is BC over OB. OB is 1. And remember, we are in the first quadrant. Everything is positive. Theta is between 0 and pi over 2. Sine is positive. Cosine, everything is positive. Okay. And as far as the arc is concerned, okay, so BC is less than AB and then less than the arc AB, which is theta, the central angle. So we proved sine is less than theta. Okay. If you divide by theta, by the way, you get sine theta less than 1. So you can hold on to that. Okay. The second part involves proving that theta is less than tangent theta. Why is that? Again, I went over that, but let's quickly recap. Okay, the arc AB is less than AE plus EB, and EB is less than ED. Therefore, it's less than AD, and AD, I hope you realize the opposite over the adjacent is the tangent. So we proved theta is less than tan theta. Okay. Now, let's put 2 and 4 together. Sine theta is less than theta and less than tangent theta. In other words, we just proved that one. Okay. Now, what is tan theta? Everybody knows it's sine over cosine, right, class? Everybody knows this is sine over cosine. Okay. So theta is less than, never mind tangent, sine over cosine. Theta is less than sine over cosine. I can multiply by cosine and I can divide by theta. Remember, all of them are positive because if they are not, it flips over the sign. In other words, I can interchange theta and cosine theta. Interchange theta and cosine theta. Okay, this is basic algebra class. Cosine becomes less than sine over theta. And so we give it number 5. So let's put number 3 and number 5 together. Okay. So cosine theta is less than sine theta over theta. So sine theta over theta is less than 1. So this expression is less than 1. Now, if we take the limit of the left side, as theta approaches 0, we get 1 because the cosine of 0 is 1. And the right side is 1. Therefore, the limit in between by the squeeze theorem is also equal to 1. Okay, everybody? Therefore, that one is also equal to 1. I hope everybody is clear on that. You're not responsible for the proof. If you can follow this, or at least spend some time to follow this, there's a lot of geometry and trigonometry involved. I hope you appreciate that. You spend some time to get comfortable with that. Let me also quickly show you the proof for this one. The limit of cosine theta minus 1 over theta as theta approaches 0 is equal to 0. We want to prove that. And the technique is to multiply the top and the bottom by an expression which is the conjugate of the numerator. If you multiply by cosine theta plus 1 over cosine theta plus 1, the numerator becomes cosine squared minus 1, and the denominator is just right. I hope you remember sine squared plus cosine squared is 1. So 1 minus cosine squared is sine squared. So the numerator is negative sine squared. Negative sine squared. All right, so we can cut this into pieces. One piece is a negative sign. One piece is sine over theta. And one piece is sine over cosine theta plus 1. So let's cut it into 3 pieces. The sine, which is negative, and then sine theta over theta, and then sine theta over cosine theta plus 1. And let's take a limit of all of it. Okay, we know this one to be 1. So with the negative in front of it, this becomes negative 1. How about this one? Well, let's plug in. Sine of 0 is 0. Cosine of 0 is 1. Okay, so let's plug in. So what do you have? Negative 1 times 0, and that is 0, everybody. Let's quickly recap this one. I forgot to record this. So we write the definition of f prime of x for sine x to prove the derivative is cosine x. We also write sine of alpha plus beta is sine alpha cosine beta plus cosine alpha sine beta. Therefore, we're going to expand the sine of x plus h. The first and the last one, we put them together. We take out the sine x and we rewrite them in this fashion. We can apply the limit laws looking like this. And we have proved this stuff. This is 0, this is 1, and practically we are done. By the way, if you look at the graph of a sine and cosine, that also shows you that the derivative of sine is cosine, okay? Let's quickly look at the case for cosine. Again, we said the derivative of cosine is negative sine. So let's do that by applying the definition to cosine x. So what is cosine of alpha plus beta? Okay, so cosine of alpha plus beta. Cosine alpha, cosine beta, minus sine alpha, sine beta. Therefore, we expand the first piece. And we do the same thing. Look at the first and the last. We put them together. And we factor out the cosine. We apply the limit laws. We separate them into the following pieces. Again, we use what we have proved, and this goes to 0, this goes to 1. This is simply cosine x times 0. This is minus sine x times 1. And believe it or not, this is the end of the proof. So now that we have proved this stuff, we can move on and look at some examples. All right. Sine t plus pi cosine t, okay? The derivative of sine is cosine, plus pi, the derivative of cosine is negative sine. Therefore, it's minus pi sine t. To differentiate this piece, first we change this one to t to the power of 1/4. And please understand this is minus 1/2 cosine t, okay? So this uses the power rule. 1/4 t to the power of 1/4 minus 1. Minus 4 e to the power of t. Minus 1/2 times cosine gives you negative sine. So with the negative becomes positive, okay? You just rewrite this and you're done. You rewrite this and you're done. Okay. Use the product rule on this piece. You can put a raised dot in between in case it helps. So x squared 2x times sine x plus sine x gives you cosine x times x squared. And you just put the x squared in front. You can factor out the x. It doesn't make that much of a difference, okay, class? But you could if you want. We want to differentiate this using the quotient rule. All right, we are using the quotient rule. The derivative of the top is just cosine times the bottom minus, what is the derivative of the bottom? 1 minus sine x, because the derivative of cosine is negative sine, everybody, times the top, and you just write the bottom squared. I hope you realize you're done with calculus. So what do? You just simplify things. And that's what we are going to do. So this gives us what? X cosine x plus cosine squared. So this gives you x cosine x plus cosine squared x. Done. Minus. What is the product of these two? 1 minus sine squared. I hope everybody remembers a minus b, a plus b, right? Now, what is 1 minus sine squared, everybody? Cosine squared. So cosine squared with a plus sign and cosine squared with a negative sign cancel each other. And we're done. Okay, so quotient rule, again, the only calculus step. Then there is some algebra and trigonometry involved.
Is there another way of doing this?
There may be other ways. What do you have in your mind?
Multiplying x plus cosine x to the numerator and denominator?
No, we are not simplifying or we are not proving anything. We are differentiating using the quotient rule.
Got it.
Because the question is differentiate. Does that make sense?
Yeah, it does.
Perfect. Again, we are doing the same thing. We are not proving anything. We are differentiating. Therefore, we use the quotient rule, everybody. We are going to use the quotient rule. Okay. All right. And again, look at the top. It's the f function. The bottom is the g function, everybody. So the derivative of the top is negative sine times the bottom. Minus. What is the derivative of the bottom? Minus cosine x times the top. And you just write the bottom squared. The bottom, you really don't have to do much. Just write it as is and squared. So let's quickly recap. The top, the derivative is negative sine x times the bottom. Minus the bottom minus cosine x. So we're done with calculus. Let's just simplify. Minus sine x plus sine squared plus cosine squared. We are simplifying, everybody. And we know sine squared and cosine squared, they add up to 1. Yes? Okay. So what happens? The numerator, class, the numerator is what? 1 minus sine x. The same as the denominator, but the denominator has exponent 2. So the numerator again is 1 minus sine x goes away, becomes 1, and the denominator loses the exponent and it becomes 1 minus sine x. Okay. Again, I hope you see that a lot of algebra, trigonometry involved. We should be comfortable with that. Okay. All right. We want to find the equation of a tangent line. Again, if it helps, put a raised dot here and therefore we are using the product. We want to differentiate this. Why? Because we want to find the slope of a tangent line. First, we need to find f prime of x. So what is f prime of x? Let's do the product rule. E to the power of x is itself times cosine x plus cosine is negative sine times e to the power of x. Negative sine times e to the power of x. It really doesn't make that much of a difference whether you factor or not. It's not important. Now we are going to plug in 0 to find m or f prime of 0. Let me just quickly show you. So f prime of 0 becomes e to the power of 0 times cosine 0 minus sine 0. E to the power of 0 is 1, cosine 0 is 1, sine 0 is 0, so the answer is 1. Now y equals mx plus b will do the job because this is the y-intercept. Y equals mx plus b, everybody. Y equals mx plus b will do the job. All right. We said the derivative of tangent is secant squared. Well, how do we know that? Let's prove it. The derivative of sine is cosine. The derivative of cosine is negative sine. We proved it. Let's look at tangent. Well, what is tangent equal to? One of them is sine x over cosine x. Of course, it's like 1 over cotangent, but another one is sine over cosine. Why are we writing it this way? We are going to use the quotient rule on this to get to the answer. Quotient rule will do the job, everybody. Quotient rule will do the job. Okay, f prime, the derivative of the top is cosine times cosine, minus the derivative of cosine is negative sine times sine. Therefore, practically you're done. This is it as far as calculus. This is cosine squared. This is plus sine squared. The numerator is 1, everybody. The numerator is 1. What is 1 over cosine squared? Secant squared. We just proved it is equal to secant squared. Okay? And I highly recommend you do cotangent on your own. We said the derivative of secant is secant x tan x. We said that. Let's look at the proof. How do you prove that? Well, secant is 1 over cosine, isn't it? We are going to use a quotient rule on that. We are going to use the quotient rule. F prime g minus g prime f over g squared. The derivative of the top is 0 times cosine x minus the derivative of the bottom is negative sine x times 1 over the bottom squared. So this goes away, becomes 0. This is negative times negative is positive sine x over cosine squared x. Now, we want to make it look like this. It's very simple. We can write this as 1 over cosine times sine over cosine. 1 over cosine times sine over cosine is exactly what we said the derivative of secant was. So this is the proof that the derivative of secant is secant tan. I highly recommend you do cosecant on your own, everybody. Okay. All right. Let's look at this differentiation. I want you to know that it could get involved, but and there may be different ways of approaching that. I'll mention that, and you're exposed to various methodology. The very first thing we have to do is the quotient rule. Okay, just the way it is. If we want to differentiate that, okay, the top, never mind, the 1 minus secant becomes minus secant x tan x times tan x minus The derivative of tan x is secant squared times the numerator in the parentheses over the bottom squared. And you're done with calculus. Now we just have to rewrite things, okay? All right, so what do we have here? Minus secant x, tan squared, minus secant squared x, minus times minus is plus secant cubed. And secant is in common. You can take the secant or negative secant, makes no difference. Either way is fine. So if you take the secant x out, you get negative tan squared plus secant squared minus secant x. So I hope you remember when we looked at Pythagorean identities, okay, sine squared plus cosine squared equals 1. Another one is tan squared plus 1 equals secant squared. Another one is cotangent squared plus 1 is cosecant squared. These are Pythagorean identities in trigonometry. So when you see that, I hope you realize if you take the tan squared to the other side, secant squared minus tan squared becomes 1. So this expression is 1. Now, if you didn't do that, it's not that big of a deal because it doesn't really simplify much. But this is one way to do that. Again, for the sake of argument, I'm going to show you a second method, okay? Sometimes people stick with a sine and cosine. If you remember when we were dealing with the proofs in trigonometry, we would start going to sine and cosine only. You don't have to do that here, you're done. But just for the sake of argument, I want to show you the second method by changing secant and tangent. Secant is 1 over cosine and tangent is sine over cosine. So if you do that, now you have a complex fraction. You have to multiply the top and the bottom by cosine x to get rid of this complex fraction. When you do that, the denominator simply becomes sine and the top becomes cosine minus 1. And now you do the quotient rule on that. That's my point. Either way is fine. Okay, everybody? Now, here's the quotient rule. The derivative of top cosine is negative sine times the bottom, which is sine, minus the derivative of sine, okay, is cosine times the parentheses, and you put the top over the bottom square. And again, this is the end of calculus. You just simplify the numerator. How? This is minus sine squared. This is minus cosine squared and plus 1. My apologies, plus cosine x. These two, they add up to negative 1. I hope you see that because sine squared plus cosine squared is 1. Because both of them are negative, they add up to negative 1. If you left it as that, it's okay, but I hope you realize the denominator is 1 minus cosine squared. And the only reason you write it because remember the denominator becomes 1 minus cosine times 1 plus cosine, and it can in fact, simplify into negative 1 over 1 plus cosine. In other words, here's the reason. Let me just write. This class can be written as 1 minus cosine x, 1 plus cosine x. And when you drop the 1 minus cosine x from the bottom, the top changes to negative 1. That's why, okay? Again, do you have to do it this way? Not necessarily, but I wanted you to be exposed to that also. So let's do more examples. We need to use the quotient rule again. The top gives you cosine times the bottom minus the bottom gives you secant squared times sine. And so how do we simplify? Let's distribute. The bottom you don't have to worry about. This gives you cosine t plus cosine t times tangent. Now, what is cosine times tangent? That is sine. I hope you realize why, okay? Because you can write this as cosine times sine over cosine. So therefore it becomes sine t, okay? And honestly, if you left it as that, okay, let me just repeat, cosine t plus sine t minus secant squared t sine t over 1 plus tan t squared, you're done. Let me just write that. If you wrote this as cosine t plus sine t minus secant squared t sine t, and you wrote the denominator, you're done. That's fine. Now, secant squared is 1 over cosine squared. You can write it like that. And then it becomes tan t times secant. It doesn't matter. So over here, it's really just being overdone. And the only reason I put it there, okay, if you want to manipulate going through the trigonometric identities, that's fine. You don't have to. As I mentioned, that is done. And you are okay with that. How about this one? The very first thing I want you to notice is that we have 3 terms. And how do you deal with the product rule when you have more than 2? Well, you got to cut it into 2 somehow. For example, we could say it is x squared times the product of sine and tangent, because the only formula we know is f prime g plus g prime f. In this case, let me write it at top of it so you see what I mean by that. Now this becomes f, and the g function is the bracket, okay? Anytime you have more than 2, you have to do it this way. So having said that, x squared gives you 2x, okay? So x squared gives you 2x times this piece. And the brackets, now we do the product rule on the brackets, okay? Sine gives you cosine times tangent, plus tangent gives you secant squared times sine. And then all of that, you put it in some brackets times x squared, okay, by the product rule. So again, x squared gives you 2x times this. The bracket gives you this thing when you differentiate. This is, let me again write at top of it accordingly. So this is f prime g plus g prime f, okay? And you're done. You just simplify, okay, class? You just have to simplify this. So let's do that. We are distributing what we have, okay? 2x sine x tan x, okay? Then we put the x squared in front for this piece and for that piece, okay? And the only thing that, again, we showed that cosine times tangent is sine. Everybody remembers that, right? I went over that. Okay, you can go back to your notes. And you can leave it as that. You're done, or you can factor out the common factor of x and sine x. X and sine x. If you didn't, it's not that big of a deal, but it is important to change this 2 into sine. You have to change that into sine. Okay. We want to find an equation of a tangent line for this guy. And again, in order to find this, you need a pair. You have it. Okay. By the way, I hope you realize if you put pi instead of x, you get pi plus tan of pi, which is 0. So it becomes pi. So you need to differentiate. Y prime is x gives you 1, tan gives you secant squared. So what is the slope? Well, plug in pi. So it's m is y prime of pi. That means m is 1 plus secant squared pi. Okay. Now, what is secant of pi is 1 over cosine pi. Let me just write that. Okay. Secant pi is 1 over cosine pi, which is, if you remember, cosine pi is -1. So 1 over -1 squared. That's the bottom line. And then y minus y1, that means y minus pi equals m, or 2 times x minus x of 1 or pi. And everybody can simplify this. This becomes 2x minus 2 pi and this is what happens. So y equals 2x minus pi. And by the way, whatever you come up with, remember, the pair that you have, it should work with the original function. It also should work with your tangent. Okay. We are
Hey,
going
Professor,
to, yes,
can you go back to that problem?
go ahead, go ahead.
How'd you get, so you got secant pi equals 1 over cosine pi
Yes,
equals over
because
negative.
secant is 1 over cosine.
How'd you get that -1 after that?
Because cosine pi is -1.
Oh, shit.
Cosine pi is, see, cosine 0 is +1, cosine pi is -1.
Okay.
So secant pi becomes 1 over -1, which is -1. Does that make
Okay.
sense?
Yeah.
And that's what we have here. And then we square that because
All
it's
right.
secant squared.
All right.
Does that make sense?
Yeah, a lot more sense. Yeah.
Perfect. Perfect. Okay. We want to look at the limits, and later on there are other ways. Again, for example, L'Hopital's rule, but we're going to stick with what we know now. And what we know is this. We prove this too. We're going to use them. Now, I want to make sure everybody understands the meaning of this. Take a look at this. The argument of sine is theta, the denominator is theta, and this is theta. If the three are identical, the answer is 1. So take a look at here. What is the argument of sine here? X. What is the argument of sine here? Pi x. What is this one? X. Okay. Now, somehow we want to make it look like this. So here's the technique. We're going to divide the top and the bottom by x. We're going to separate the top from the bottom. This is using the limit laws. Now, what I want you to pay attention, I don't want you to look at the bottom yet. The top is the limit of sine x over x as x approaches 0. Just the top. Look at the top and the top only. This is the same as this one, and the top is 1. Now take a look at the bottom. Take a look at the bottom. What is the argument of sine? Pi x. What is the denominator? Not pi x. So what is missing? Pi. Okay. So if I had pi, I would be in good shape. So why don't I put a pi here? That means I'm dividing. How do I undo that? I have to multiply it by pi. So take a look at why I put the pi and why am I putting it in a different color. Okay, everybody? Pi and pi. So this can get out of the limit sign. And now look at this bottom limit. This is pi x, this is pi x, but this is not. However, when x approaches 0, pi x approaches 0. So take a look at what happens here. I'm going to just write the numerator. The denominator pi is just a multiplier. You can take it outside the limit sign. The top has pi x as the, remember, you can never ever touch the argument of sine. That's not what we are doing. So it's pi x, this is pi x, but I'm changing the x here to pi x. How can I do that? If x goes to 0, pi times x also goes to 0. Now this is 1, this is 1, so you have 1 over pi as the final answer. You really have to go over these questions a couple of times to make sure you're comfortable, okay?
So what you're saying is you can interfere with the rule under the limit
Now, the thing is, you cannot change the argument of sine. Notice, you see this one is pi x. You can never change that because
Right.
that's the argument of sine. But what was the denominator? Well, originally the denominator was x. We want to make it look like pi x. How? I can multiply by pi and divide by pi. Notice this pi and this pi cancel each other. So I'm not changing anything. In essence, I'm multiplying by 1. Do you see that? And that's important to see. And then this pi is a multiplier. If you take it out or not, it makes no difference. You're concerned with this part. The argument of sine doesn't change. Now, the denominator is just like the argument, we're in good shape. But this is not. Okay, that's not good. However, because x approaches 0, pi x approaches 0, so that's good. Now, this thing looks just like that. You can, in fact, call it theta, and this goes to 1. Now, again, the couple of pages that I'm going to do, you need to look at them again, class. I can't emphasize this enough. Here's the next one. We don't have that, but let's see the technique involved. This doesn't look like any of this, but the numerator looks like the numerator here, and the denominator looks like the numerator here. Why don't we divide the top and the bottom by theta? It's okay, right? I hope everybody can see that this expression is equivalent to this expression. I'm dividing the top and the bottom by theta, and I'm going to apply the limit laws. Now this, we know it to be 0, and this, we know it to be 1. 0 over 1, the answer is 0. Okay. Now, here's the next one. Again, I want you to see that what is the technique involved to fix the problem. We don't know the answer to this just the way it is, but we notice that we have x squared in the denominator, okay? And perhaps we can separate this into sine 3x over x. This is sine 5x over x, okay? And then this guy has 3x, so we need 3 here, and this has 5x, we need 5 in here. How do we create that? So take a look at what happens. Number 1, we write the x squared as x and x. Number 2, because this is 3x and this is not, if I change this to 3x, that means I'm multiplying by 3, then I'm going to multiply the top by 3. Notice they can cancel each other. This is sine 5x. I need 5. So now, this piece, I can take the 3 out. This piece, I can take the 5 out. Take a look at what happens. We are applying the limit laws. In this case, because the argument of sine is 3x and the denominator is 3x, I'm going to change this x to 3x. Why? Because if x goes to 0, 3 times x goes to 0. If x goes to 0, 5 times x goes to 0. Why am I writing it in this fashion? Because going back to this, I have to have the argument of sine, the denominator, and this one identical for it to work. So now it's 3 times 5 equals 50.
Hey, Professor, can't you just substitute it and just say, like, let u equal the argument?
Yes, of course you can. Yes, of course. You can let, in this, just as an example, for this part, you can let, let's say, theta or u, as you said, it doesn't matter, to be 3x, that's fine. So what you have is, if I want to just look at this part, if I want to just look at this one, sine x, so the limit, let me just look at this one, sine x, sine 3x over x, okay? So what you have here, if you want 3x to be u, you can write it in this fashion, okay? So you can say the limit of a sine u, and this becomes what? One third u. And remember, this is x, and you have to go back to 3x. You can do that. Yeah, you can do that. Here's another example. We have the limit of cosecant x times sine of sine x as x approaches 0. All right. I can put the cosecant at the bottom because cosecant is what? Cosecant by definition is 1 over sine. So I'm going to take the cosecant down. I hope everybody understands what happened here. Cosecant is the same as 1 over sine. So take a look. You just mentioned the substitution. So if you let sine x be theta, then if x goes to 0, sine x goes to 0, right? We can write that. X goes to 0, sine x goes to 0. So let sine x be theta. This is the substitution you just mentioned. And therefore, we can rewrite it as such. And that's equal to 1. With the substitution, we get to the answer. All right. How about this one? Remember, you just have to use what you already have proved. That means these two. Okay. If this was sine x over x would look like this, but it's not. And what is the argument of sine x squared? Can you touch that? Absolutely not. But can you change this to x squared? Yes. How? Multiply the bottom and the top by x. So I'm multiplying the top and the bottom by x. And then I take out the x. So I have the limit of x as x approaches 0, the limit of sine x squared over x squared as x approaches 0. Because x goes to 0, so does x squared. So this is the same as this one, and it's equal to 1. This is equal to 0. The product of 0 and 1 is simply 0. And that's it.